All right, well, here we are back at the train station, at Einstein's train station. Of course, we have Einstein's thought train, a train that can travel from left to right at very, very high speeds, according to this guy here, who is our stationary observer. But, of course, in the frame of reference of the dude in the train, what he actually thinks is happening is this guy is travelling from right to left at very high speed. Now, our train is equipped with our trusty light bulb, although this time we've connected it up a little bit differently. Because there's a couple of other features that we have on our train. First of all, down here at his feet, we have a mirror to reflect the light. A light pulse is going to be sent down, and we have this device over here, which is our light sensor. And when the light beam arrives at that sensor, it's going to go beep, and it's also going to set off another pulse of light. And so effectively, what we've got here is a light clock. So we send a pulse of light down, it hits the sensor, sets off a beep, sends off the next light pulse, and it's a way of measuring time. So we're going to compare what time is like for the person in the train compared to the person on the platform. Now, because all the clock and its mechanism is in the frame of reference of this guy, when we talk about this guy's time, we're going to talk about that as T0. And that doesn't mean that he's not moving and the other guy is. What it means is that the event that we're observing occurs in his frame of reference. So now we want to consider, well, how long would TV be? Well, we know very simply that speed is distance divided by time. And now the distance from the top of the train carriage to the bottom of the train carriage is simply L. Okay, so it's going to travel two lots of L. Let's just rearrange this so that we know that time, T0, is going to be distance divided by the speed. So the distance is 2L divided by the speed, which is, everyone's going to agree, is the speed of light, that's c, and that gives us our very important equation for what time, how long the time would be from the point of view of the guy in the train. Let's have a look at what it's going to be from the point of view of the person on the platform. Okay, so let's just get rid of all of this for now, and let's think of this not from this guy's point of view, but from the point of view of the guy on the platform. So the train is over here, and what he's going to see is the train going past him as a light pulse is sent down, and we measure this time interval. Because we're measuring it from the platform guy's point of view, we're talking about TV. What that means is the event we're observing is in the frame of reference that's moving relative to him. It's not in his frame of reference, it's in the other frame of reference. Okay, so let's step ourselves through this. Our light pulse comes on, and we're just going to make a little mark every sort of frame that we're going to move this on so that we can trace the path of the light ray as it goes down, hits the mirror, and goes back up again. Now already you can see, remember we're looking at this from the point of view of the guy on the platform, already that you can see that this is going to be taking a longer distance to get there. Now, because it's travelling at the same speed, c, because everyone agrees upon the speed of light as being c, we can see that what's had to happen is the light pulse has taken that pathway there, which you can immediately see is a longer pathway. So let's have a look at exactly how much longer that pathway is and what the time would be. Well, how far has the train moved between there and there? Okay, well, the speed of the train, let's say the train has some kind of velocity v, is simply distance divided by time, and so we want to know what distance has the train moved on. So we just rearrange this equation. So distance equals the velocity times the time. And remember, we're talking about the time according to this guy down here in the moving frame of reference. So the distance is going to be simply v tv. So this distance here is v tv. That's the distance between there and there. And of course, the distance between here and here is simply L. And so we want to know what this path length is. Well, let's think about things from the point of view of the light beam. What's the total distance it will travel? Well, speed equals distance over time again, and we want to know what the time is. So time equals distance divided by speed. Okay. Sorry, let's work out what the distance is. So distance equals speed times time, which is going to be equal to c tv. Okay, so the distance down this line and back up again is going to be CTV. Now, how are we going to work out what CTV is? Well, we're simply going to go, this is like two right-angled triangles, and we can use Pythagoras' theorem to work out how to calculate what that length is. Okay, so here's our triangle representing the distance that the light ray has travelled, and we know that the distance that the light ray has travelled is going to be CTV. That's the distance the light ray has travelled, which of course is the journey down here and the journey back up there. We know that we can use Pythagoras' theorem of c squared equals a squared plus b squared. And we're going to use Pythagoras' theorem to work out each of these triangles as a separate entity. Okay, so we can look at each of those, and of course then the total path length is going to be twice the hypotenuse of one of those. So we can say that the distance is going to be equal to 2 lots of the square root of a squared plus b squared. Okay, so let's have a look at what that is. Now remember, from over here, our distance is CTV, so CTV equals twice the square root of, okay, well one side here is L and the other side over here is CTV divided by 2, right, because we're talking half the distance there. So we've got L squared plus CTV on 2 all squared. And so now we're starting to get somewhere. All right, here we are to do the algebra side of it. If this is all a bit hard to you, you don't actually need to derive these. You could probably just fast forward to the end. But I actually think it's worth having a look at where they come from. We tend to think of relativity, really heavy mathematics. Actually, it just comes out of speed is distance divided by time and Pythagoras' theorem. It's really not that hard. It's just that the algebra gets a little bit tedious, and you probably couldn't guess where you're going unless you know where you're trying to get there, which is probably why it took a few years for it to be worked out. Anyway, let's work on this one here. Let's first of all take the 4 inside, the 2 inside the square root bracket, which is going to make it 4, outside of L squared plus. Now let's just square this TV squared on 4, and instantly you're going to see that that 4 cancels there. It's going to be 4, so that gives us the square root of 4L squared plus V squared TV squared, and this is CTV. Let's square both sides to get rid of that square root bracket, plus V squared TV squared. I'm going to take that last term over to the left-hand side, so C squared TV squared minus V squared TV squared equals 4L squared. We'll take out the common factor of TV squared. Let's give ourselves a little space here. TV squared outside of C squared minus V squared equals 4L squared. Let's just take the C squared minus V squared, turn that to the other side. We've got TV squared equals 4L squared on C squared minus V squared. And this is where it gets really weird, and you're not supposed to be able to guess how we're going to get there. But we're going to take out a common factor over the bottom, which doesn't really look like a common factor. It's actually going to make it more complicated. We've got 4L squared on. I'm going to take out the C term out of this. The C term, C squared term out of this, which is going to give me 1 minus V squared on C squared. Okay, so now we're getting very, very close to here. We're going to take the square root of both sides. So that's going to give us TV equals 2L all on C times the square root of this term, 1 minus V squared on C squared. Now we're getting very, very close. What we need to remember is what T naught is equal to. So if we go back up to the top, T naught is 2L on C. So if I was to substitute in T naught, have a look. T naught is there. It's 2L on C. So that means that TV is going to simply be equal to T naught divided by the square root of 1 minus V squared on C squared. And there we've got our Lorentz transformation for the time. The person on the platform is going to see the time slowed down or dilated, and the time's going to get slowed down or dilated by this term here, which is the Lorentz term. Okay, and you can see that at velocities, garden variety velocities, normal velocities that we experience, then that term is so close to being 1, so they both measure the same time. But when V squared gets to some significant fraction of the speed of light, then that term becomes quite significant. So if an event is happening in another frame of reference, you're going to see that event running slow, and it's perfectly mirrored. So both of you are going to look at each other's clock and seem as though their clock is running slow. You are going to see their clock run slow.